is Kashyap Mawani, and this is my video presentation for assignment 3. So let's get it started. So the assignment 3 is divided into two parts. The part A is basically of image convolution, and the part B is the neural network training part. So I'll start with part A. Essentially what we will do is, for the image convolution, we'll import all the necessary packages and libraries that we need. We will also import the image that we are trying stuff on, and then we'll show how it is in the visual context. It looks something like this, and then we'll use the byte IDs and image RR to get the stuff from the image that we downloaded to plot a graph for it. Right now we have gotten a pretty good Lamborghini for it in orange color, and it's spread across the graph just to get a basic idea of how we're going to use it in a context of training, right? So first what we do is we essentially load an image from the internet. In our case it's a Lamborghini, and then we convert it right here into grayscale. Right now we only deal with one color. That essentially is easier for us to get numbers out of it, so that's the whole point of converting it into grayscale, to be very honest. So grayscale, what it does is gets us this image from this. So when we are doing this, when we are using this image, we only have one color. Like I said, it's easier to process, it's easier to get our numbers on those and to do. Second, what we will do is, on convolution with 2D kernels, what we essentially do is we create a padded array by adding 2 rows and 2 columns each, and one at each beginning and another at each end. So we are kind of creating a kernel which covers the entire position of the map, and then we compare both the arrays to it. So we know our original array in this case was 140 into 359, and the padded array which we created is 142 and 361. So like I said, we add 2, one at the beginning of each, one at the end of each, right? So 140 becomes 142, 359 becomes 361. Now when we apply those kernels and plot the resulting array of it, we get the grayscale one here, as you see. Now what I did here was I applied different filters, also known as kernels. Different kernels, these kernels are like small 2D grids of numbers. Basically they are numbers, and as they move over the image, like each pixel wise, this is a graph so it's kind of hard to show, but like as it moves to each pixel, it basically is a result of multiplying the kernel by the essentially underlying pixels. So what we do is, when we convert it into grayscale and we use different kernels, we are just getting one, like we are using the number we get from one pixel from one kernel, and we multiply it by the underlying pixel and the number we get from that kernel. So we have two kernels doing 2 pixel data and multiplying them, so we get a more accurate data on 1 pixel, and we do the same process again. So for the other pixels as well, example of these filters are like we do a blur, we can do a sharpen it, we can do edge detection, which basically highlights the lines and edges of the image. This image here is a 45-degree line detection, which would give us the lines as it says. This, for instance, is a 135-degree line detection, right? And we apply these kernels to all different things, and you can see there's quite small difference, but there is difference between edge detection using kernel 2 and kernel 1. We have more lines in kernel 2, and when we use 3 Laplacian, you can see there are more broader or more clear lines in kernel 3. So that's basically how we are like kind of putting it out there. So the part A, basically I'm concluding it by saying that the different type of kernel, or in instance a different type of kernel numbers, we can produce a wide variety of effects, and that is, I think, the basic idea behind most of the computer vision algorithms. Now as for part B, we will again import all the libraries that we need and we will prepare our data set, load it, encode it again, convert it from integers to floats, pretty basic stuff, and we'll build a neural network model, right? Now we are also using max pooling, and I'll get to it, but first we'll flatten it as always, and we'll use our activation, in our case ReLU and softmax. Once the model is compiled and we display a summary of model, this is our model summary. We come back to customer callback for like logging data and stuff during training essentially. Now we will train the entire network with 50 epoch, and batch size is 256. We'll keep our verbose to 0, and this is the basic one. Now after training, the model setup is somewhere the code builds a simple neural network as you've seen, and possibly with convolution layers like the filters we just talked about, but learned automatically by the network. We don't have to manually enter each one of them. So when we are plotting the result, you would see that the result plotted down there are the accuracy curve. So essentially that blue line shows the training accuracy, which is going pretty up, and the validation would be saying pretty consistent throughout the plane, right? So that's the thing. So now the question arises, is it overfitting, and if so, in which epoch? And I've wrote the answer, but in short I would say that after each 20 epoch the model starts to overfit, and that is basically the trade-off we have between training and validation accuracy, because somewhere down after 20 epochs it messes up. As for the question 4, we have different type of layers. In our case we were using max pooling, and in this we are using conv2 to convert into 2D image, max pooling 2D, flatten it, densing it again and again. And going forward, since we are low on time, this is the compilation of new models. So we got the data of training and validation from this, and now we're going back and we're making a model to be more accurate. So we, based on that data, we feed our data set into network, and during training the network adjusts its internal weights to reduce its error and potentially improve the accuracy of the entire model. So in the monitoring phase we watch the training accuracy and the validation accuracy. So in simple words, it means like how well it does on the data it sees versus how well it does on the new data. And by the end of the training, this is the result of those terms, and you could see that the improvements in both accuracies is there. We might also see if the network overfits, it learns too much from the training data but fails on the new data. So this graph, as I showed you here, and the earlier graph which we see on top, has the different accuracies, and it's very clear that it is getting higher with every result, right? So compared to original, the larger model, it's much higher training accuracy, significantly faster, reaching to 90s compared to earlier one, right? Now this model is again a new one based on the last two models we create, but the difference is we are adding a dropout in this one. Now by the end of this training and with this model, what we would see would be the improvements in both accuracies. We might also see, there's a chance we might also see if the network overfits, that is if it learns too much from the training data but fails on the new data, which is common. But with dropout there's something new to happen, and you can see the training data and validation accuracy jumps over. It's way easier, it's going way straightforward, and it's very effective regularization strategy, and it's like it's helping avoid overfitting essentially. And this is my answer for the last question. Since this is too much for the time, I'm gonna cut it here. Thank you very much. My name is Kashyap Mawani, and this is a video representation of assignment 3.